Okay, in this tutorial we're just going to go over relative mass and molecular formula and things like that. So if I just have a look, bring up the periodic table, let's just grab it like this. Yeah, I'll leave it there, so then we can talk about carbon. I want to talk about carbon a little bit. So this is carbon. I'll just change the colour a little bit. So here's carbon here. Now, if you look at the other tutorial, we've mentioned the atomic number, this one here, and we've mentioned the mass number here. And if you look at the mole and Avogadro tutorial, you'll know that this relates to the number of particles. But the way we determine the rest of the periodic table and set a standard, if you will, and calibrate all the masses is we adopt carbon 12 as the default atomic mass. Now, I'll just get rid of periodic table a second. Actually, I'll leave it there a second. If we look here at carbon 12, it's not quite 12, it's 12.011. So it's not actually set as 12. They used to use hydrogen as 1, and then anything else could be added up based on the weight, the mass of hydrogen. But because carbon's more abundant in terms of it's not more abundant in the universe, but it's more abundant in the life forms that we have. It's easier to get a mass for carbon. So that's why hydrogen has got a relative mass of 1.0079, and that takes into account all the other isotopes are in there as well. So if you look at the isotope tutorial, you'll see what I mean by that. But I'm just going to bring up carbon again, so we can have a look at carbon, and then you can see what I'm talking about. Just get rid of these. So I urge you to have a look at your periodic table and just see what these numbers relate to. Now this is carbon 12, so this is defined as having a mass of 12. Now mass is different to weight, because weight is basically the mass times the gravitational field strength. Okay, so that's the strength of gravity, if you will. So that's weight. So when you step on a weighing scales, you're actually getting some indication of your mass, your actual mass, how many elements you've got present in your body, all added together. But if you went on the moon, that would be slightly different, but your mass would be the same. You'd still have the same number of particles, but because gravity on the moon is different to on the Earth, you'd actually look like you were lighter, and that's simply because you'd be measuring your weight and not your mass. So that's weight, and that's mass. Okay, now they are different, but in general usage, in a non-scientific way, mass and weight are more or less used the same as the same word, but they're not the same word really. They are very different. So we look at carbon now, the carbon 12 here. We know, if you look at the isotope tutorials and Avogadro's number tutorials, you'll see that the carbon 12 is made up of 6 protons and 6 neutrons, giving it atomic mass of 12. Now if you took one atom of carbon, then you would have to basically add, let me just do this, you'd have 6 protons, 6 neutrons, and you'd have 6 electrons. You'd have to weigh them all together. See, I use the term weigh then. You have to work out the mass, which you could do by weighing, and if you knew the gravitational field strength, and then you'd be able to come up with a number, and that number would be incredibly small. Okay, so it'd be 10 times 10 to the minus 27 kilograms, and that's really tiny. So if you weighed all them you get an incredibly tiny number, and that's where Avogadro's number comes in and the mole comes in to give us this value here, which is 12, which represents 6 times 10 to the 23 times this, just to give us an everyday mass that we can relate to. So basically, I'll just get rid of these now. Basically, all we have now, just grab these to one side, is the mass of, let's get rid of these as well, the mass of carbon on Earth as defined in the periodic table will be 12 grams per mole. 12 grams per mole. Okay, so if you took some graphite or diamond, if you had 12 grams of diamond, you'd be very lucky, but if you had 12 grams of diamond, then that would be 1 mole, and that would be, if you look at Avogadro's tutorial, you'll see what that means. So how does this help us as a chemist? Well, if we take water is a very good example. So take water, I'll just change the colour of the pen. So take water here, and given that carbon's 12, we now know that hydrogen's got a mass of 1, oxygen's got a mass of 16, so the molecular formula for water equals H plus H plus oxygen. That's how many elements are present there, how many atoms. And then if we put the mass number of that, 1 plus 16 equals 18. So we know that the molecular formula equals 18. So that's the mass for the molecular formula. There's a mass. Okay, and that is really useful if you, I'll just scroll this down a little bit, if you actually I'll leave that on there, you can see carbon up the top, might help. I'll just get rid of this and this, and that's really useful if you've got something like a sugar. Well, let me just make a molecule up just to try and illustrate a point here. If I draw this structure here like this, I'll draw it like chemists would draw it. So don't worry about the way I'm drawing it. You don't have to learn how to do this just yet. I'm just putting all the hydrogens on so you can see them. Put that as a CH3. Okay, that's a hydrogen. Each point there, sorry, I've got to put 2 more hydrogens on there, haven't I? H. Okay, so each point there is carbon, and that's the way chemists draw these structures. Okay, it's a bit like a sugar. It's not quite sugar. So we add all these up. We've got 1, 2, 3, 4, 5, 6 carbons. That's C6, and then we add all the hydrogens up, so we've got 3 there, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens, 12 hydrogens. How many oxygens have we got? We've got 1, 2 oxygens. So that's the molecular formula for this compound here. Now I've just made this compound up, but imagine we wanted to add a certain amount of this to something else, to water for example. We wanted a 1-to-1 mixture of this compound and water. Now it would be very important to get the mass of this right, because then we'd know exactly how many moles we had, and we'd know how many particles we had, so we can get the 1-to-1 ratio of that. So in order to work out the molecular mass of this, we'd have to times this by 12. So it'd be, the molecular mass would be for carbon, 6 times 12. Then we need to add, so that's for carbon. Then we need to add hydrogen, and that'd be 12 times 1. And then we need to add for the oxygen, that's hydrogen. And then we need to add, sorry, that's 2, isn't it? 2 times 16. Now where these values come from, let me just change the colour of my pen. So this value here, okay, and this value here, that's the times, that looks like a 7 but it's a times, and this value here, yeah, they're the atomic mass of the elements. Okay, just draw oxygen there in red. So now we know there's 6 carbons, 12 hydrogens, 2 oxygens. So what does that come out to give us in terms of its mass? And that's just a matter of adding these up. So that'll be 72 plus 12 plus 32, and that equals, let me just write that, 116. So that is the molecular mass of this molecule that I've just made up. So that's how we determine mass, and it's all based on 12 for carbon. There's carbon 12. But if you do look in your periodic table, because there are slightly different versions of elements called isotopes, and these isotopes just got extra neutrons, they might have 1 more or 2 more or maybe 1 less, 1 fewer, sorry, then that slightly skews the weight, sorry, the mass. See, I'm saying weight and mass as well. So that slightly skews the mass that is given in the periodic table because of this. There are also some other factors that change the mass, and that's called binding energy, and we'll do that in another tutorial, and I'll try and link that up to this tutorial. So I'm going to stop there, but I'm going to extend this tutorial to a part 2, and then we'll look at how we can detect the mass, actually how we know that the masses are of given values. So that's relative mass compared to carbon. So if you remember in part 1 of this tutorial, I went on about molecular mass determined from the mass of each element that we use. Instead of using the particles, the number of particles, we use moles, and the moles is basically a certain number of particles, so 6 times 10 to the 23 particles, so atoms, that's not very good at all. 6 times 10 to the 23, let's do that again. 6 times 10 to the 23 atoms of carbon equals 12 grams, and that's only for carbon 12 though. So carbon 13 would be 13 grams, carbon 14 would be 14 grams, and so on. Now the actual mass of carbon is averaged. We take what's called an average mass. So let me just get rid of this compound that we worked on in the last part of the tutorial. So sometimes we take the average mass, and if we work that out, we have 98.9% is carbon 12. So if we just took carbon, say we got graphite or even diamond, then in the let's use diamond, actually, it's a good example. If we take diamond, 98.9% of it, so 98.9 of all the 100 carbons that are present in a 100 carbon crystal would be carbon 12. So 98.9 is percentage equals carbon 12, and 1.1% equals carbon 13. And that's why, if we just get the periodic table, drag it across again, that's why we get this value here, because the mass of carbon is slightly a bit more than 12 because we've got this carbon-13 hanging around as well. Okay, so that's where we get the mass like that. So that's the average mass, really. Okay, so that's carbon-13 and carbon-12, and isotopes. There's one trace of that, so that doesn't really come into the equations much. So how do we detect these? How do we know that these different masses exist? Well, if you remember from the nucleogenesis tutorial, where I discussed J.J. Thomson. Well, J.J. Thomson was actually the first person to detect electrons, and he used a cathode ray tube, and he also went on and looked at other masses of other elements too, using this method. And this method turns out to be one where it's been developed a lot more since. But this method, this is what I've drawn, and you'll find similar pictures in textbooks. I'm just going to walk you through it. This is called a mass spectrometer. So just write that down for you. Mass. Whoops. Mass spectrometer. Now, what this does, you take your sample. Say you've got a sample of, I've still got a copy of this compound I made before. So say we've got this compound. I'll just, oops, shouldn't have done that really, should I? So we've got this compound anyway, and if you remember, it had a mass of 116. Yeah, so it's formula weight, I'll write as FW. Now this is sometimes called different things as well. It's called MR, relative mass, and all this. So let's write that as well. MR equals, or sometimes M big R. So formula weight, relative mass, is 116. Okay. Now what happens if we take that sample, we put it in here, we've got to heat it up, or we've got to make it volatile. Okay, so it's like turning it into a gas, because this will be a solid probably. So we make it into something that's volatile and it can travel then, you see, and this is a vacuum in here. Okay, so it's had all the air sucked out of it, and as it passes through here, it's bombarded with electrons, or it could be some other source. There are other methods, and if you look in the tutorials on spectroscopy and things like that, you'll come across mass spectrometry. And I urge you to look at them, all different forms. It doesn't matter for this, because what really matters is this becomes charged, because it'll lose an electron or gain an electron or whatever. Okay, so it gets charged. So you get this molecule, and now it's got a charge. So let's imagine it's positive, it's charged. Just for this exercise. Okay, so this gets positively charged. Now, as it goes through there, it gets bombarded with this charge. It doesn't have to be negative, it can be positive, and I've made it positive here to confuse the matter, but it doesn't really matter. It gets charged, so you now got a neutral molecule, goes through here, comes out here as a charged species. Now charges are deflected by electric and magnetic fields. Okay, now it's also got a lot of energy, it's got a lot of kinetic energy, and it will be whizzing through there. It's a bit like because this is a vacuum, this is a bit like a bullet being fired from a gun. And as you know, as a bullet gets fired, or if you throw a ball, it's going to eventually go to Earth due to gravity. Okay, so this is eventually going to be deflected and hit something. It would go off in a straight line, but these magnetic fields here bend the charge, they attract it and they drag it round, and as they're dragging it round, it actually separates the different weights, or different masses should I say. See, I'm always saying weight. The different masses. So imagine if we had this molecule here, and I'll just delete this a little bit here. Imagine we had this molecule here, and then we had some, I don't know, some impurity, which was very, very similar. But instead of that, C H. Say it was NH, NH2 actually. That's a good one. Imagine we just got that instead. Just draw that down there. That's a CH3. H. 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 Okay. So now we've got, rather than a OH there, and that bit there would have a mass of 16. I'll draw this in a different colour. That would be 16 and 1, and this one would be 14 and now 2 plus 2. Okay, so there's only a little bit of difference there. So you've got 17 stuck onto this carbon, or you've got 16 stuck onto this carbon. Now this is that sensitive of a technique, it will be able to distinguish between these two molecules. So this is our formula weight of 116, and this has got a formula weight of 115. And it would be able to detect the difference. And it was actually J.J. Thomson who first detected the first isotope using a technique very similar to this, and that was for neon, I believe. So it's an incredible machine and very, very sensitive. You only need a tiny, tiny amount of material and you'll be able to detect all the different molecular weights in there. So that's mass spectrometry. So that's how we know about mass. But again, this is all, if you go back to the first part of this tutorial, it's all determined relative to carbon being 12. If we'd set carbon as being 6 or any other number, then all these would be shifted by that amount too. So carbon is set as carbon 12 is 12 as a number. That's how much the mass of carbon is. And so from that we can work out the formula of small molecules like this, large proteins, and so on and so on and so on. And this is a very useful technique. Mass spectrometry is a very useful technique to be able to determine what compounds are present and what the molecular weight is, what molecular mass is. There I go again. So hope you enjoyed this tutorial, and look out for the other ones. I'll put links in that will link to mass spectrometry. If you're interested in that, you can go on to further investigate that, and also there'll be several more examples and problem sessions on working out molecular masses, moles of compounds, and how much materials to add in reactions and things like that. So that is relative mass.